All right. Hello, everyone. Feels weird not wearing a mask in the room, but there's no one else in the room today, so I will be talking to you. And the lesson we are going to be looking at today is on how you factor quadratics and then something called a perfect square. We're going to talk about both of those things. If you remember from yesterday, quadratics is the main focus of this entire unit. So this word here especially is going to be important in today's lesson. We are going to start off though by doing some review. Back in Algebra 1A, we learned how you would multiply these. Go ahead and distribute this first one. If you need a quick refresher when you are distributing, you're going to multiply x with everything in the second parentheses and then the 2 with everything in the second parentheses. So when we do that, x times x is x squared. X times that minus 3 is minus 3x. And then when we multiply the 2 times x is 2x. And then 2 times that minus 3 is negative 6. Looking at that, there is one more thing you can do. These terms right here, we can combine. We can say, well, negative 3 plus 2 is negative 1. So we can say negative 1x, or just minus x, and then bring down that minus 6 there. So that's one of them. If you needed that refresher, make sure you go ahead and try the second one. Pause the video and try it now. Alrighty, that second one, when you multiply, would give you b squared minus 5b minus 4b plus 20, which when you combine those middle terms would give you minus 9b. So b squared minus 9b plus 20. The reason I wanted to start off by reviewing this is similar to yesterday. This is something we learned back in Algebra 1A in our polynomial unit. We learned how to take this multiplication problem and multiply it all out to get this answer here. Also, just like yesterday, what we're doing today is going in reverse. So we know how to distribute, we know how to multiply this and get to this part here. What we're doing today is we're given something that looks like this, and we want to factor, which remember factor means rewriting it as multiplication. So we're going to be taking expressions that look like this today and rewriting them to look like this. Same over here. I could give you something like this and ask you, can you represent it as multiplication? Our answer would look like that. Now you might notice looking at this that these look different than what we were doing yesterday. Yesterday we were factoring with GCF, or greatest common factor. Today we're factoring in a different method. So before we get into any of these factoring problems, I want to talk about these two ways we're seeing to factor. So starting off with what we're going to be looking at today. We call what we were just looking at factoring into binomials. You remember back from our polynomials unit, binomial, well, bi means 2. Binomials means 2 terms. So when you're factoring into binomials, it looks something like that. They're going to be 2 parentheses and then 2 terms inside each parentheses. So something like x plus 3, x minus 2, something like that. When you are factoring into binomials, the reason it would look like this is if it is a quadratic, which remember is the name of this unit. Quadratics are any expression or any math problem you can write in the form ax squared plus bx plus c. What that means is focusing in on those x's. It means there's an x squared, an x, and then a, b, and c are numbers. So this would be like an x squared, an x, and then a number at the end. That is the same thing we just saw a moment ago when we were multiplying this out. If you remember, we got, it was x squared minus x minus 6, I think. That right there is an example of a quadratic. We've got an x squared, an x, and a number. The variables might be different, so maybe instead of x's, it's, I don't know, a through z, any letter you want. But the idea is the same. If it's in this form, we call it a quadratic. So what that means is if you have a quadratic like this, you're going to be factoring it into binomials. So as far as examples go for quadratics, we've got this example here. Some of the examples we'll be looking at next week also have numbers in front of them. So something maybe like 6, we'll change the variable to 6b squared plus 3b minus 11 could be another quadratic. But anything in that form where you've got your variable squared, variable, number. We factor with greatest common factor pretty much for everything else. With greatest common factor, it's going to be if you have a polynomial that is not a quadratic. And that polynomial is going to have something in common, hence greatest common factor. So notice some of the ones we had yesterday were things like 10x cubed plus 5x squared. I think that's one of the ones we looked at yesterday. Notice that this is not a quadratic because we don't have x squared, x and a number, and they've got something in common. They both have 5 in common and x squared in common. That's a clue you would use greatest common factor. You might also use greatest common factor if you have multiple variables. So something like, we'll do 24a squared b plus 12ab minus 10ab squared. Perfect, something like that. Notice they've got multiple variables. They all have a and b in common. They all have a factor, a number factor that you could factor out that they have in common. These are examples of cases where you would want to use GCF. It can kind of be tricky at sometimes because sometimes problems look really similar to quadratics. So maybe like we'll do c squared minus 3c plus 5c cubed. It's close. It started off looking like that, but if it's not in this form, it's not a quadratic, which would mean we would want to use GCF instead. So I want to talk through this first. Today, all of our problems are going to be quadratics, but moving into the future, I'm not going to always give you a quadratic. I might give you a mixture, and you've got to be able to look at it and know which way we're going to factor. Now that we've got an idea of what quadratic expressions look like, let's talk about how we factor them. So we said earlier, give me a second to erase this. We said earlier that a quadratic would look something like this. We've got an x squared, an x, and a number. And we said when you factor quadratics, you're factoring it into two binomials, so two sets of parentheses. What our goal is, because it's important I think to remember the goal, is I'm looking for something that when I multiply all of this out, it gives me this right here. One of the first things you can fill in is the only way I'm going to get an x squared there is if I have x and x. X times x gives me that x squared. So that's one of those terms I can fill in. The other part here is numbers. I'm looking for a pair of numbers that when I multiply all of this out leaves me with 10x plus 16. Well, the thing you know about these numbers here is these two numbers at the very ends, that last step when you're multiplying out, those two numbers should multiply and give you 16. So our next thing we're going to do is we're going to write all the different pairs of factors that can give you 16. If I'm thinking about pairs of numbers that multiply to 16, I think it helps when you go in order with these. So I'm going to start off with 1 and then go 2, 3, 4 until I run out of pairs. I'm going to think 1 times 16 gives me 16. What about 2? 2 times 8 gives me 16. 3 times, nope, because there is no 3. That could multiply by something, by a whole number to give you 16. 4? Well, 4 times 4 gives you 16. If I keep going, 5, no. 6, no. 7, no. 8 is already on my list. That tells me I've got all the different pairs of factors. So I'm looking at this. These numbers are going to have to be one of these 3 pairs. These are the only 3 options that when they multiply will give us 16. The way you decide which one you're going to use is you are going to choose the pair of factors that can combine to give you that middle number there. I'm looking for a pair of factors that multiply to give me that 16, but can combine, and I'm using that word combine because depending on the signs, that combining might look like addition or it might look like subtraction, but that can combine to give me 10. Do you see which pair of numbers that is? It's going to be this 2 times 8 here. 2 times 8 gives me 16, and if I were to add the 2 and the 8, it'll give me 10. The last step here is filling in those numbers and then figuring out what signs we would need. So one way you can do that is asking yourself that same question. What signs would we need here so that those numbers multiply to give me a positive 16 and so that they add to give me a positive 10? Because everything's positive here, it's easier to see that they're both just going to be positive. Positive 2 times positive 8 gives me positive 16, and 2 plus 8 gives me positive 10. When there's negative signs, though, it might require a little more playing with. The last part of this, it's not a step listed here, but you guys know how much I love checking at this point. This is a problem where you can check your answer. Do you have a guess how we could check? What is that? Are you telling me to multiply this back out? Then yes, you are correct. When you're factoring, just like we were doing yesterday, these two things are equal. They should be the same. I'm just changing the way they look. So if I were to multiply this back out, it should look like this. We're not changing what it says, we're just changing the way it looks. So my check is, let's actually multiply this out. When we go to multiply, the first thing we're going to do, well, x times x. X times x gives me x squared. Remember, that's why we started off by filling in the x times x. X times x, we said, is the only way I'm going to get that x squared. Got my x times x, I can say x times 8 gives me plus 8x. And then I'm multiplying my 2, so I would say 2 times x gives me 2x. And then the last part, 2 times 8 gives me 16. Remember, that's where this step here came from, is we said we know these two numbers here are going to have to multiply to give me 16. Now the last part, if I look at this, there's something we can do. We can add the 8x and the 2x to give me 10x plus 16. And that step right there is where this part here is coming from. We said we're looking for two numbers that will combine to give you this middle term, because when you multiply them out, you're going to end up combining them to get that middle term. Again, I think especially since you are at home right now learning these, knowing how to check your answers is really important. Because just like yesterday, if we get something that is not what we started with, it means there's something in that factoring that we need to change or tweak to get the original expression. It could be a sign. Maybe one of our signs are wrong. Maybe we chose the wrong pair of numbers. But in doing this, you'll figure out if they're equal, it means we factored correctly. If they're not, it tells you, I need to go in and change something. So this was my first example. I think we'll try 2 more and then I'll have you try some. For this first one here, see how much you remember. Do you remember what the first thing is we did? Well, it's a quadratic. I know that because it's x squared, x number. It's in that form, ax squared plus bx plus c. So because it is a quadratic, I know it's going to factor into 2 parentheses. What can we go ahead and write down? Well, to get that x squared, I know it has to be x times x. How are we going to figure out these numbers here? Well, those two numbers are going to have to multiply to give you 24 and combine to give you 5. When we think of different pairs of numbers that multiply to 24, well, if they multiply to 24, it could be 1 times 24, 2 times 12, 3 times 8, 4 times 6. There's no 5. And the next would be 6, but 6 is already there, so I've got them all. This is like a real good example of why I think it helps to go in order. It makes you know you've got all the different pairs of factors. I've got this list. Which one are we going to choose? Well, if I know they need to combine to give me a 5, the only one that's going to do that is this one right here. I'm going to have to combine them using subtraction. That idea of knowing you're going to need subtraction tells you there's going to be a minus sign or a negative sign somewhere. The 3 and the 8 will fill into these parentheses. A question I usually get when there's students in the room is, does it matter which way those numbers go in? Can I write 3, 8, or do I have to write 8, 3? What do you think? The order is not going to matter, and it goes back to this idea of, does the order with multiplication problems matter? Is 3 times 8 and 8 times 3 the same thing? Well, yeah. So it's the same idea here. I've got this times this. It doesn't matter which order you put those parentheses, just as long as you have them both. What is going to be important, though, are our signs. What signs would I need on these numbers here? Remember, you're looking for a pair of numbers, including the signs, that multiply to negative 24 and combine to positive 5. Sometimes this step of choosing what signs you need can be challenging for students, so I like to remind people you really only have 4 options here. It's going to have to be a 3 and an 8. So the 4 options are either they're both positive, they're both negative, that first one's positive and the second one's negative, or the first one's negative and the second one's positive. There's only 4 combinations. So if at any point you're struggling to figure out what is that combination of signs I need to make this true, you could go ahead and just write down what I did there and see which combination is going to give us that positive 5 we want. And the magic combination that does that is this one here. It is a minus 3 and a positive 8. So you could write this down, or you could write down that. You could switch around the order of your parentheses. The last part, if I wanted to check to make sure this is correct, what could I do? Well, we could multiply it all back out. When you do that, x times x, x squared, x times the 8, plus 8x, and then negative 3x, negative 24. That last step, when you combine these, you do in fact get that plus 5x. One last one. What's the first thing I could do? Hopefully you're writing down 2 sets of parentheses, putting your w's. I know it's going to start off that way because this is a quadratic. W squared, W number. Next thing, we want to find a pair of numbers here to fill in. That pair of numbers needs to multiply to 16 and combine to 8. Some people, especially people who've just have a lot of experience doing this, don't need to write out that list of factors. So you might know just from that description, I know what pair of numbers multiplies to 16 and combines to 8. If not, that's totally okay. You can just make yourself a little list. We are all at different places of our math journey. Either way is going to lead you to the same pair, which is 4 and 4. Because 4 times 4 can give me 16. And if I combine them using addition, it'll give me an 8. Can you figure out what the last step is? Well, that last step is figuring out what signs you need. What signs would you need here to multiply to a positive 16 and combine to a negative 8? For this one especially, I see a lot of students starting off with 2 plus signs because they know, positive 4 times positive 4 gives me positive 16. But the problem with that is 4 plus 4 gives you 8, not negative 8. If we want a negative 8, we're going to need both of these to be negative. Negative 4 and negative 4 gives me negative 8. And then when you multiply negative 4 and negative 4, it gives you positive 16. There are 2 down here at the bottom. Guess who those are for? They're for you. This first one here, you're going to factor g squared minus g minus 30. Go ahead, pause the video and try that now. This one here, sometimes it's tricky to students. You got to remember there's a 1 right here. So when you go to factor it, we've got our 2 g's. the pair of numbers that multiplies to 30 and that combines to 1, you're going to subtract to get that 1. You're going to subtract a 6 and a 5. 6 times 5 gives you 30, and then if you subtract 6 and 5, it gives you that 1. If we're looking for a negative one when we combine, that means the 6 needs to be negative, the 5 needs to be positive. And then that last one there, factor x squared plus 3x minus 10. How'd you do? Did you check your answer? It's not too late. You can always pause and check if you did not. When you factor this one, you should get x plus 5, x minus 2. I know that works because 5 times negative 2 is negative 10. And a positive 5 minus 2 gives me that positive 3 I'm looking for. So this was the first part here. This is factoring quadratics. Now remember, there was 2 parts to our goal for today's lesson. One was we wanted to talk about factoring quadratics. And then the second part was we wanted to talk about factoring something called a perfect square. So to help me introduce that second part, I've got 2 more review questions. Again, you're going to simplify these by distributing. Go ahead and try that now. Alrighty, this first one here, when we go to multiply it up, same as what we were doing for those other ones. X times x, we're going to say x squared. X times that 3 gives me a positive 3x. Then here, negative 3 times x is negative 3x. Negative 3 times positive 3 is negative 9. That last part of this, I see 2 things I can combine. When you combine positive 3x and a negative 3x, 3x minus 3x, what happens there? Well, those cancel. 3 minus 3 gives us 0. 0 is nothing, so that's why we say they cancel. That means they leave the problem. There are no more x's in my answer. Sometimes students are tempted to put down, the 3's cancel, so I'm left with an x. 3 minus 3 is 0, means our answer needs 0 x's. No more x's. So all that's left is that minus 9. If you have not already, go ahead and try this other one. That other one there, when you multiply it all out, you'll get t squared minus 7t plus 7t minus 49. And then when you go to combine, we get t squared, the negative 7t and the positive 7t cancel out. And again, we're just left with that minus 49, t squared minus 49. Now the questions I like to ask here are, what is similar about these 2 problems? And how are they different from the other ones we've been doing? Some of the things I hear in class is they're similar because they both only have 2 things. Those 2 things are called terms. They both have 2 terms. 1 term, 2 terms, 1 term, 2 terms. That's different from the other ones because all the other ones have 3 terms. That's why you're thinking, why is that? Why do these only have 2 terms? Well, they only have 2 terms because in these 2 problems, that middle part there canceled out both times. That's why there's only 2 terms instead of 3. That didn't happen in any of the problems we did before. Well, why is that? Why did something cancel here and it hasn't canceled out yet in any of our other problems? What's special about what we started with? Well, these 2 problems, the reason something canceled out, it canceled out because we had a negative 7t and a positive 7t. Up here we had a negative 7 and a positive 7. Same thing over here. Positive 3, negative 3. Positive 3, negative 3. All of those previous problems, we always had like different numbers here. Notice for both of these problems, it was the same number in different signs. Sounds like our lesson on systems. Remember, to cancel something out, we need the same number in different signs. Same number in different signs. Now there's a reason I'm pointing all of this out. Remember what our goal is today. This is distributing. Our goal is to factor. So what that means is I'm going to give you something that looks like this, and your goal is to get back up to this. Well, both of these problems here look different than what we had before. We said earlier they only have 2 terms. When you see something like this, there's something you know. For it to have looked like this, those middle terms would have needed to cancel out, which means same number, different signs. You can go through all the same steps we were doing before and you will get the same answer, but this is kind of like a trick or a shortcut based off of what we observed from these two problems. So with that, I'll erase these. Instead of me doing this first one, I'm going to have you try it. This first one here, go ahead and try to factor it and see what you get. Two ways you can think of it. Again, it is a quadratic, so I know I've got my two parentheses here. I can say, okay, well, I know z times z gives me the z squared I need. To get that at 25, we could always come over and write out the factors of 25. 1 and 25, 5 and 5. Notice that middle term there is missing. It's missing. It's a 0. Which one of these could I combine to get a 0? Well, that 5 and 5. Just like we had noticed earlier, those numbers are going to end up having to be the same. What signs would I need? Well, if they're going to multiply and give me a negative 25, I'm going to need a positive 5 and a negative 5. For something new like this, I would definitely want to check. If I multiply it out, we get z squared minus 5z plus 5z, and then minus 25. And then just like those distributive property questions we were looking at, the negative 5z and the positive 5z will cancel out, leaving us with z squared minus 25. Ta-da! You have figured out how to factor this. These problems here are called perfect squares, or perfect square quadratics. Way back in pre-algebra, we learned perfect square numbers are those numbers or those products you get when you multiply a number by itself. So for example, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4, 5 times 5, 6 times 6. Obviously, we can keep going. But these are our perfect square numbers. So these are perfect square quadratics because it's involving all of those numbers. And it's using all of these numbers because of this idea that these numbers would have to be the same for that middle term there to cancel out. So using all of this incredible knowledge you just gained, you're going to go ahead and factor these last two for me. Go ahead, pause the video, try this one. What about the other one? All right. This first one here would be w minus 6, w plus 6. Also, like we said earlier, it doesn't matter the order. So you could have w plus 6 times w minus 6. It's up to you. And then over here, you would want something like that. X minus 7 times x plus 7. Now with these perfect square quadratics, there is one last stage to make them even more fun. I'm going to challenge you even more. What about these problems? What if it looks like this? Similar to last time, I'm going to challenge you, pause the video, try to figure out what we would need to write for the multiplication problem to end up with this as your answer, using all of the stuff we've talked about so far in this lesson. How'd you do? Well, similar to the last time, notice there are only two terms. That middle term there would cancel out. Usually when I'm watching students struggle with this in class a little bit, trying to figure out what it has to be, what we've done in the past is we've always started with an x times x. And we were doing that because x times x gives us x squared. But the problem is I don't want x squared, I want 4x squared. That means there's going to have to be a number in front of that x to give me 4x squared. Sometimes students will try something like a 4x and an x, and then to get that 25, they'll say what we were doing before. We need a positive 5 and a negative 5. The problem with that So when you go to multiply it out, you have 4x squared. When you multiply these, you have a positive 20x. But when you multiply these, you have a minus 5x. That's not the same, so they're not going to cancel out. For these to be the same, I need to be using the same pair of numbers. So I cannot go 4x and x, because that's going to give me different results when I multiply. What we can do instead, do you know what I'm going to write? Is 2x times 2x. If we try that, 2x times 2x gives me 4x squared. 2x times 5 gives me 10x. And then negative 5 times 2x gives me, did I say 10x? 10x and then minus 10x. And like that, because I'm using those same pair of numbers, now I have something that will cancel out. To finish it up, the negative 5 times the positive 5 is negative 25. These would cancel, and we're left with 4x squared minus 25, which just makes you oh so happy, because that tells you that your answer is correct because they're equal, they're equivalent to each other. Now that you've seen an example, I'm going to have you go ahead, pause the video again, try this one. For this one here, I know I'm going to have a z and a z to get that z squared. To get 36z squared, we need to use a 6 and a 6z. 6z times 6z gives me that 36z squared. For that 144, I'm going to have my positive 12 and my negative 12. Because I'm using all the same numbers, it means when I go to multiply everything out, those middle terms will cancel and leave me with this. Don't believe me? 6z times 6z gives me 36z squared. 6z times negative 12 is negative 72z. And then we have a positive 72z. And then the 12 times the negative 12 gives me negative 144. And just as we were predicting, those will cancel out, leaving me with what I want. One last one for you. All right. This last one here, what you are looking for is an 11D and 11D. And then for that 49, it would be a positive 7 and a negative 7. And ta-da, you are quadratic factoring experts. There is one last slide to this lesson, and that last slide we're going to look at some other ways this skill can be asked. For example, I could tell you that the area of a rectangle is 100b squared minus 49. Just a reminder that we use that little, it's called a caret, but we use it to show when something is an exponent. So that says 100b squared minus 49. So the area of a rectangle is 100b squared minus 49, and one side length is 10b minus 7. What is the length of the other side? If you feel like you know what to do, pause the video, try it. Sometimes in class, it's hard to know how you're going to approach this problem. Like, what are they asking me? What do I need to do? There's some things I'm going to point out. We are talking about the area of a rectangle. When I see those words, I would pause and ask myself, well, what do I know about the area of a rectangle? Usually in class, I'll hear, well, area is the space inside something. Great. Do we know how to find area of a rectangle? Well, you find it by multiplying the sides. You're using that formula, area equals length times width. This is going to be important in understanding what this problem is asking. So what are they saying? They're saying the area is this. So we know the area. We know the area is 100b squared minus 49. We also know something else. We know the length is 10b minus 7. So I know this part here. The length is 10b minus 7. What we're trying to find is the length of the other side. We're trying to find what this other part here is. Once you've got it set up like this, it's easier to see, well, this is what we were just doing. We're trying to rewrite something. In this case, this polynomial here, the 100b squared minus 49, we're trying to rewrite it as a multiplication problem. The difference is, here I gave you half of it. All you've got to do is figure out what the other half is, but I didn't even need to give you this. I could have told you this is the area. what's the length and the width? In order to find those two things, you're just looking for what two things multiply to give you this. That's what factoring is. Factoring is figuring out what it looks like as a multiplication problem. I think we've broken down here what we need to do. Go ahead and see if you can figure out what our width is. Well, a couple ways you can kind of approach it. You can figure out, well, 10b minus 7, what would I need to multiply that by to get this? Or you could just use what we've been doing with factoring. It would end up being another 10b, so that those multiply to give us the 100b squared. And then to get that minus 49, I would need a positive 7. So what is the length of the other side? The other side is 10b plus 7. Sometimes you'll also hear the word factor with these. These are each a factor of 100b squared minus 49. So that was my example. Here's the one you are going to try. How'd you do? So for this one here, if I set it up the same way we did this earlier one, I know my area is my length times my width, or some people say breadth, or length times breadth. Our area we've got is n squared minus 14n plus 48. So I'm trying to figure out what we would need to multiply to get this. Well, I know to get that n squared, I'm going to need n and n. This goes back to the first quadratics we were factoring. I need a pair of numbers that multiply to 48 and combine to negative 14. That might not immediately be obvious to you. 48 has got a lot of factors. Factors of 48 are 1 and 48, 2 and 24, 3 and 16, 4 and 12, 5, no, 6, yes, 6 and 8, 7, no, and 8 is already there. You too can write lists of factors this quickly. It's just a matter of spending a lot of time doing multiplication problems in a math class because I am a math teacher. But this is what I would want if you can't figure out what pair of numbers you need here. I think doing this is very helpful. Once you've got this, do you see which pair of numbers we would want to use? Well, which pair gives you a negative 14? I'm looking for a pair that I could add in this case to give me 14. That would multiply to give me 48. So here I could put down my 6 and my 8. For them to combine and give me negative 14, they would both need to be negative. And I know that works out because negative 6 minus 8 gives me negative 14. And negative 6 times negative 8 gives me positive 48. Both of those things have to be true. So to answer the question, what are the lengths of the two sides? I could say the two sides are n minus 6 and n minus 8. Ta-da! You have done a lot of factoring today. Remember, please reach out if you've got any questions on these. We would love to help you. Hopefully you're feeling better about factoring. What we're doing on Monday is more factoring of quadratics, so you want to make sure you're feeling pretty good about factoring these. That'll put you in a really good place for what we're doing on Monday when the fun continues. Thanks so much for watching. Bye!